Good morning, students. Today we are going to continue with the solid state second part. Today I am going to show you first the characteristics and structures of different types of crystalline solids. There are four types of solids which we have to learn in detail. They are ionic solids, example sodium chloride, covalent solids, diamond and graphite, metallic solids, copper. Let's see the detail about their structure using some diagrams. Look at this diagram. This explains the structure of sodium chloride. We call it ionic solid because it is made of ions like sodium and chloride ion. Now, what is the arrangement of these two ions in the unit cell? First, let us try to find it out. Please look at the big cube. Ignore these two portions. You can see these green dots. They are representing chloride ions, and red dots, they are representing sodium ion. Now look at the arrangement. Here you can see at the corners as well as at the face center, these green dots are present. So we can say the arrangement of the unit cell is a face-centered cubic unit cell. And the other positions are taken. Here you can see the edge and body center taken by the sodium ions. If you look at the smallest cube as you see here, you can see in the smallest cube the alternate corners are occupied by the sodium and chloride ions. That's why this smallest one we don't take as the unit cell because it is not uniform here, because alternate corners only are occupied by one type of particle. Next, so it is face-centered cubic unit cell. Next, how many are surrounding each particle? Now look at first the sodium ion. If you look at now this diagram, you will find the sodium ion is surrounded by 6 chloride ions. So these 6 chloride ions, you can say, are the nearest neighbor of sodium ion. Similar manner, you can see here each chloride ion is surrounded by 6 sodium ions. So here the nearest neighbor is for sodium and for chloride same 6. This is called the coordination number also. And here as two different types of particles are present, we call or we say their coordination number as 6:6. Why? 6 for sodium and 6 for chloride. And if we consider their structure, the crystalline structure, not the unit cell, it is octahedral. You will understand it better if we try to solve a question. See this. From this portion, this type of question we normally get. What is the question? for a crystal of sodium chloride state. Number 1, the type of, it is lattice, printing error, the type of lattice in which it crystallizes. Number 2, the coordination number of each sodium ion and chloride ion in the crystal lattice. Number 3, the number of sodium ions and chloride ions present in a unit cell of sodium chloride. And number 4, the structural arrangement of the sodium chloride crystal. The first one we have already discussed, CCP or FCC. Remember, face-centered cubic also can be mentioned as cubic closed tab. Second one, coordination number, as I have told you, 6:6, because there are two types of particles. Only one number is not enough to explain it. Here you see the value, I will explain it with the diagram. 4 sodium ions and 4 chloride ions are present in each unit cell. And the structure of the crystal is octahedral. Now let us go back and see how we calculate 4 sodium ions and 4 chloride ions. You can remember in our previous class I have explained how to count the number of particles present in simple cubic unit cell, face-centered cubic unit cell and body-centered cubic unit cell. But here there are two types of particles present. So here the calculation is not as simple as what we have learned in previous class. Let's see how can we find it out. First, look at the chloride ions present at the corners. Obviously there are 8 corners, and we know the particles which are present in the corners are contributing 1/8 to a particular unit cell. So 8 of them, 1/8 each. So total contribution is 8 multiplied by 1/8. So 1. Besides that, we have 6 chloride ions present at the 6 faces. Middle of the or center of the 6 faces. And what we have learned in the previous class, each face is shared by 2 cubes. So half of each is actually the part of the unit cell. 6 of them are there. So 6 multiplied by half, we get 3. So altogether 1 plus 3, 4 chloride ions present in the unit cell. Now look at the sodium ions, those red dots. Red dots are present at the edges. Please look at this particular red dot. You can see this line, the edge, is actually shared by 1, 2, 3, 4. 4 cubes. So each edge is shared by 4 cubes. So any particle present at the edge contributes 1/4 of it for that unit cell. So how many edges are there here? 1, 2, 3, 4, 5, 6, 7, 8 and 9, 10, 11, 12. 12 of them. So 12 edges, 1/4 of it gives us 3. And in this entire unit cell you can see 1 particle is at the body center. So completely belonging to that particular cube or that particular unit cell. So altogether 3 plus 1, 4. That gives us the answer that 4 sodium ions and 4 chloride ions present in 1 unit cell of sodium chloride. Next, structure of diamond. We know in organic chemistry we have learned that carbon atoms are having tetracovalency. Here you see these all dots are carbon atoms. In diamond, look at this particular carbon atom. There are 4 other carbon atoms around it, tetrahedrally arranged. Another point we need to remember, the carbon atom is sp3 hybridized here so that it can form 4 covalent bonds with 4 different other carbon atoms. But now look at this. Here this is not one molecule only. This carbon again shared by 4 others. This one again shared by 4 others. And the structure grows in all 3 directions, giving us a macromolecule as diamond. Now, the types of question which we get from here. In a crystal of diamond, how many carbon atoms are present per unit cell? I will explain it a little later. Next, what type of lattice does diamond crystallize in? Here it forms a face-centered cubic structure. Next, how many carbon atoms surround each carbon atom? Obviously we have seen 4 of them. And how are they arranged? They are arranged in a tetrahedral manner. Now, why do we call it face-centered cubic? If we this tetrahedral arrangement and we want to fit it inside a cube, then you will find the alternate corners are occupied by the particles. Altogether there are 8 corners. So 4 corners are occupied by the particles and 1 particle at the body center of the cube. That gives us the tetrahedral structure. Now when we have 8 such cubes arranged together, then we will find it gives us ultimately a face-centered cubic arrangement. That's why we call its unit cell is face-centered cubic. Calculation of number of particles are slightly complicated here, but whatever it is, as we can see there are face-centered cubic, it's supposed to give us 4 particles. But I said in case of diamond there are 8. Where those extra 4 particles coming from? Those 4 particles are coming from the middle of the alternate cubes. Because I have told you already that when we see the tetrahedral arrangement in a cube, there are alternate corners occupied by the dots and 1 at the center of the cube. So alternate cube will have 1 particle at the center that contribute to 4. So altogether 8 particles we get. Next we come to graphite. Please try to get the structure. First look at only this portion. You can see those blue particles which are carbon atoms are arranged in hexagonal manner. Each carbon atom is linked to 3 other carbon atoms. So remember here, this carbon atom is sp2 hybridized with one pure p orbital left, which is placed in a vertical position on this plane. So all these carbon atoms are sp2 hybridized, and each one of them are having one vertical p orbital, pure p orbital. So this forms one layer, next another layer, next another layer. So layer by layer they are forming the structure. And between two layers, yes, those vertically placed pure p orbitals are overlapping with each other, and electrons are there to bind those layers. But remember, they are not forming a pure covalent bond like this. So these bonds are stronger, but the interaction between the layers are weaker. As a result, the layer can slide over each other. That's why the graphite is soft and having greasy film. Not only that, as these vertically placed pure p orbitals are occupied by one electron each, so they have place to jump from one orbital to another orbital and can move from one end to the other. As a result, they can conduct heat and electricity. Here I think I can explain one property which I have told you in the previous class very well. That is anisotropic property. For crystalline solids, we have said that there are some properties which are anisotropic. Here we see the electrical conductivity through graphite is anisotropic in nature. How to explain it? Look, electrons can move from one end to another along the plane or parallel to the plane, cannot move vertically through the planes, because electron can jump from one p orbital to next one, to next one, to next one, to move from one end to other. But through the plane it cannot. As a result, here electrical conductivity is good along the plane but not perpendicular to the plane. So what we have learned, in some direction it is good, but in some other direction it is not at same magnitude. So here you can see electrical conductivity is not same in all directions. That's why we say electrical conductivity is anisotropic in graphite. Next one, we see copper. Copper also you can see, this is the unit cell. Don't look at this first. This is the unit cell, and we have one particle at the corner, one particle at the face center. So it has face-centered cubic structure. Now as it is face-centered cubic structure, simple. So we know how many particles are there in one unit cell and other points. Nearest neighbor. Now look at this diagram. If we see this particular copper atom, 1, 2, 3, 4, 5, 6 on this plane, 3 above this plane and 3 below this plane. They are the nearest neighbor of this particular copper atom. So, What is the coordination number or the nearest neighbor of a particle or a copper ion in this structure? It is 12. Look at the question. Again, related to diamond. For a crystal of diamond state, the hybridization, I explained it, sp3. The coordination number we have already discussed. The type of lattice in which it crystallizes, already done. And the number of carbon atoms present per unit cell, that is also done earlier. Next. Compare the crystals of copper and diamond, giving one similarity and one difference. See, first similarity. Copper and diamond both are hard, have high melting point, have face-centered cubic or cubic closed-packed structure. See the difference. Copper crystals contains metallic bonding, are good conductor of electricity, has coordination number 12. How 12? I have explained using the diagram. On the other hand, diamond crystals contain covalent bonding, are non-conductor of electricity, has coordination number 4. Yes, these are the common type of question we normally get during